So far, everything that we have done has only looked at something that is being dropped or thrown straight up in the air. What we're going to look at now is when you shoot something or kick something or throw something and it's moving in both the X and the Y direction. If you look at the red line in this picture, it is a line that just shows the motion if there were to be no gravity. If you look at the black line, is the motion if there is gravity alone and when you don't have any sideways motion. The black line is what we've done so far. If you look at the blue line, is what you would see if you kick something or throw something off of a cliff. In this case, it shows the path due to gravity in black going down, the gravity-free path that's happening in the X direction in red, and the blue line is what you would actually see in that situation. What we'll be looking at over the next week is how we can use what we know in the X direction, like the red line, and what we know in the Y direction, the black line, how we can use those things to figure out what's actually happening with the blue line. In this picture, it shows you what's happening both in the X direction and in the Y direction. If you look at what's happening in the Y direction, it's over on the left-hand side, you can see the ball falling, similar to what we did with the water dropper. The farther it goes down, the farther apart the drops got, and in this case, the farther apart each ball gets. In the Y direction, the ball continues to fall like that. If you look in the X direction, there is no acceleration, so it moves at a constant speed across the top. The combination of these motions is what we see in the line that shows how it would normally fall. So if you throw a ball, you would see it fall along that middle line. It's a combination of what's happening both in the X direction and in the Y direction. In the Y direction, acceleration stays at 9.81 meters per second squared, and in the X direction, there's nothing to make it go faster or slower, so that speed stays constant. So let's say you have a ledge that's 10 meters high. And from that ledge, you're going to kick a ball straight off. And that ball is going to fall at some point on the ground that happens to be 25 meters away. Everything we've done up until this point is always just in a straight line, and now we're going to get into 2 dimensions. What happens is gravity still acts on the ball and pulls it in the Y direction, just like it does if you were to throw it up or down. And in the X direction, there's nothing to accelerate it. And so we can treat these as 2 separate situations and calculate them likewise. So we're going to have a chart that we're going to make, and it's going to have our distance, our VF, our VI, the A, and the T. We're going to look and see what's happening in the X direction, and we're going to look and see what's happening in the Y direction, and then we can use that information to solve our problem as a whole. For the problems we'll be doing, the acceleration in the X direction will always be 0. There is nothing causing that object to speed up in the X direction, so as it's going across this way. In the Y direction, gravity is the only thing that's pulling it down, so our acceleration there is 9.81 meters per second squared. We'll always use positive on this for what we're doing this week. The other thing that happens in the Y direction is it starts in the Y direction with an initial velocity of 0. Right here, the ball is not falling down, not falling down, not falling down, and as soon as it doesn't have anything to support it, only then does it start to come down. And it accelerates like that. But before that, the initial velocity going down is 0. There is an initial velocity, but it's only moving in the X direction. X is always going to be side to side. Y is always going to be up and down, just like on a graph. Well, now we can take this other information and put it in. If we look here at the height of our ledge, that's going to be 10 meters high. And because it's going up and down, it's 10 meters high in the y direction. Here at the bottom, it's going side to side. It's going from the base of the ledge over to where it lands, and it's 25 meters, and that's in the x direction. Now we have information to start to solve our problem. In the x direction, we just know the distance and acceleration. We don't know how fast it's going. We don't know the time. We don't know any of those things. If we know the time, then we can use that information to figure out the VI that we're looking for. In the y direction, we know the distance it's going to fall. We know the VI, we know the A, and we're looking for the T. In any problem, you'll have enough information in one of the columns to solve for the T. The T is the same in both columns. It only hits the ground once. So what we'll do is we'll use the y column and the information there to figure out how much time the ball was in the air. So in the y direction, we'll use the equation d equals VIT plus 1/2 AT squared. The thing that's happening in the y direction is that your VI is 0. This whole thing can go to 0. So you have the distance in the y direction is equal to 1/2 AT squared. Well, we want to solve for time. So I'm going to multiply both sides by 2 and get rid of that half. I'll divide both sides by a and bring the a over to the other side. And then I'll need to take a square root to get rid of that squared. That gives me the equation that t is equal to the square root of 2 times d over a. You'll get really good at this process because a lot of times we'll be using something like this. That time, if I put the numbers in there now, square root of 2 times my distance in the y direction, which is 10, over my acceleration of 9.81. And when I do that, I end up with 1.43 seconds. This is when the ball hits. It hits both in the x and y direction. It doesn't hit differently for different directions. So I did that in the y. That's what I have there, but because it hits once, I now know the time in the x direction as well. Now, in the x direction, I can figure out how fast it's going. I'm going to start with the same equation. D equals VIT plus 1/2 AT squared. However, now I'm using the variables in the x direction. These for the y won't help me with what I'm doing here. I know in the x direction that my acceleration is 0. Well, 0 times anything gives me 0. So this whole thing goes to 0. So I have D equals VIT. Well, to solve for the VI, I'm going to divide both sides by t. So I have VI in the x direction equals D over t. In this case, the distance in the x direction is 25 meters. And the time, the same as in the y, is 1.43 seconds. And we end with 17.5 meters per second. So anytime you have a problem like this, you'll use one column of information to solve for the time. And once you have the time, you'll use it in the other column to solve for what you're looking for. In this case, we solve for time using the y column and use that time to solve for VI. 17.5 is what we're looking for. There's no question about the VF in here, and it's not needed, so we can leave that blank. We will do more practice of this over the next week. There are 3 situations you'll be looking at. Sometimes you'll know your VI, and you'll know your height, and you'll need to solve for where it landed. Sometimes you'll know where it landed and your VI, and you'll need to know your height. And sometimes, like in this problem, you'll know your height and where it landed, and you will need to know your VI. We will go over this considerably on Monday and give lots of various examples.